Princeton, professor Serhian Princeton was looking at Haldane, and after he went to Stanford to work with Tushin and Jean-Christophe Hewson, and now he's will be starting as faculty at Rice University.
Okay, thanks very much, Igor, for the introduction and also for inviting me here. It's my first visit to Stockholm, which is truly a great city, and it's a pleasure to be here. Okay, so there have been lots of talks recently on the cold atoms field. So right now we will change topics and talk about metals and superconductivity. Okay? Well, there was a talk yesterday on metallic states as well. So this is going to be yet another one of those talks, and it's going to also be followed by Zlatko's talk, which is also going to be on a related topic. Okay, so the topic that I have in mind is based on recent work that I did in collaboration with Steve Kivelson and Doug Scalapino. And I'm going to talk about superconductivity in the repulsive U Hubbard model. Okay? There's been tens and thousands of papers written about this, but you might wonder is there anything new I'll have to say? And hopefully the answer to that is yes. Okay, so for those of you who may be interested, this paper I'll be presenting is published in PhysRev B this year. And there's another work that's in the stage of being written up. So let me begin the talk with just an overview. Okay, this is going to be extremely familiar to everyone. Just to make sure we all understand, I'm talking about superconductivity, which at least experimentally is defined as a state of zero resistivity below some Tc. And usual superconductivity involves the interaction between electrons and phonons, which phonons act as a pairing glue and effective attractive interaction between electrons. And below Tc, a gap opens to electronic excitations. So what you have here is a Fermi surface, a gap about the Fermi surface. This gap causes things like exponential attenuation of the specific heat, etc. So the conventional pairing mechanism is we think of electrons coupled to, say, phonons, longitudinal phonons. We have some screened Coulomb interaction. We have some screened phonon couplings. And the point is that, with phonons, what they can do is you can scatter electrons at low energies but large momenta about the Fermi surface. And for frequencies close to this resonance, you can have a net attraction. I'm not going to go into the details of electron-phonon theory. I'm not interested in that in this talk. So let me just state that the Coulomb interactions get overscreened, and there's an essentially momentum-independent attractive interaction. Okay? So let's think about what happens with a momentum-independent attractive interaction, like say a short-range attractive U Hubbard model, for example. It has basically the same physics. We simply introduce some cutoff, say the Debye frequency, below which the interactions are attractive. And so what we imagine is a scattering process in the so-called Cooper channel, in which you have electrons at k and minus k about the Fermi surface. They scatter into other states which are also nested at k plus q and minus q, and that's represented by an effective interaction like this, and that's the attraction. Okay? Well, so there's this well-known Cooper instability, because when you have a Fermi C and attractive interactions, the ground state is unstable. The reason for that is because you can't neglect. So the bare scattering, you can't simply take it at that level. You have to look at multiple scattering, and if you look at this double scattering process, which is of order u squared, you see that it diverges logarithmically at low energies. That is to say, for electrons near the Fermi surface. So when you see this log divergence, you can't neglect this higher order scattering, and in fact you have to take an entire sum of these ladders, which produces a non-perturbative effect, namely that there's a new scale in this problem, which is the Debye frequency times some exponential 1 over the interaction, and this non-analyticity can only be obtained by summing over an infinite set of diagrams. Okay? So that's the Cooper instability, which everyone here knows for sure. Okay, So that's what happens in the usual case. And so as a consequence of this phonon-based mechanism, what we usually have is some S-wave superconductor with a homogeneous gap in the Fermi surface, momentum independent. It's usually insensitive to impurities, so there's Anderson's theorem, and there's never any magnetism lurking. I mean, take the example of lead, it simply becomes a superconductor. Okay? As I mentioned, specific heat and so on. And what you have is if you take a junction of this superconductor, you will not have any spontaneous currents. You'll have the usual Josephson effect. Okay? So that's basically some phenomenological properties of usual superconductors. But we want to understand in this talk something different, which I call unconventional superconductors, which have properties that cannot be summarized like this. Okay? Yes.
Helium-3 conventional superconductor?
What?
Helium-3 isn't it conventional superconductor?
No. I would say definitely not. I would say it's a strongly correlated unconventional superconductor. Because it's not a phonon. I mean, to get spin triplet superconductivity, you can't get it from electron-phonon coupling. Phonons have nothing to do with the spin states of the electrons. Moreover, it's not an S-wave.
Yeah, well, that's why I was asking.
Right.
It's not, my understanding that you can try PCS theory, can't you?
Oh, yeah, sure. The pairing mechanism for an unconventional superconductor can often be BCS. There's no I'm not saying that unconventional superconductors are non-BCS superconductors. In fact, most superconductors we know are BCS superconductors.
Okay. You're saying just some glue, the glue is unconventional, non-phonon-like. That's your definition.
So I'm going to be more specific in a minute, but I'm going to call any superconductor unconventional if it transforms under, say, the point group transformation operations in a non-trivial way. So an S-wave transforms as an identity under the point group. Okay, but say helium-3, well, if you had a p-wave superconductor like strontium ruthenate on a lattice, it transforms in a non-trivial way. It's an odd parity, for example. D-wave, that's found in the cuprates, etc. There is a caveat. There are these new iron-based superconductors which are S-wave, but let me go on. Okay, so examples are, as I said, the cuprates, where you have antiferromagnetism, superconductivity, there's this mysterious pseudo-gap, etc. And the superconducting state is actually well understood. It's so-called D-wave, in which this is the Fermi surface, or at least by symmetry, equivalent to its Fermi surface. And the gap has this D-wave symmetry in which it changes sign upon a 90-degree rotation. Okay. Other examples are this 115 systems, which have, in their phase diagram, you can tune it with pressure and temperature, they have antiferromagnetism, there's superconductivity, and you can apply pressure and tune this TC. You also have phases in which magnetism coexists with superconductivity, competes with superconductivity, etc. So you can see that TC goes up as antiferromagnetism goes down. So this is something, if you look at this, you will say that whatever is happening, we know that electronic mechanism is responsible for magnetism. And you see a phase diagram evolving like this, you can't help but suppose that electronic mechanism is also responsible for superconductivity. Okay? Come in. Okay. Another example is spin triplet superconductivity, such as strontium ruthenate. It's likely to be a time reversal broken px plus ipy superconductor. It breaks inversion symmetry and time reversal. There's another example, UPT3, which is apparently an S-wave superconductor, although I don't know much about this. It's a hexagonal system. It has multiple phases in the superconducting region itself. Okay, so these are what I mean by an unconventional superconductor. And let me say this. So for an unconventional superconductor, if you take the gap function, okay, and average it over the Fermi surface, it's going to be much smaller than if you look at any point on the Fermi surface where the gap takes its maximum value. Okay? The examples I've given, it's actually 0, but I changed this to be 0, from 0 to be much less than delta max because of these new iron-based superconductors, which I think are also non-phonon-based. I think that's well understood. Okay, so they have competition with magnetism. They have phase diagrams that you can tune with doping or pressure. Some of them break time reversal symmetry. Some of them have non-trivial topological properties that are related to quantum Hall states, etc. I'm not going to concentrate on that, but there's interest to understand these superconductors partially for this reason. And what I want to say is that there's a fairly reasonable consensus that the repulsive interactions between electrons, not the attractive electron-phonon coupling, these repulsive interactions which act on the scale of the bandwidth are likely to be the origin of superconductivity. Okay? So if you want to understand superconductivity from the repulsive interactions, you write down the simplest model you can imagine. That's the Hubbard model. Okay, so I'm going to forget about Coulomb interactions, and I'm going to think about some electron system with some kinetic energy and some short-range on-site repulsive interactions. And this was proposed by Phil Anderson to be the minimal model for the Coop rates, for example. However, this model cannot be solved for arbitrary u in dimensions greater than 1. There are quantum Monte Carlo methods which have the sign problem. So what can we do? So many people have tried to do various things, and what I'm going to do here, which is not the first attempt to do this, of course, but I try to present a well-controlled weak coupling solution of this Hubbard model for an arbitrary d greater than 1 system on a lattice, or in the continuum. And I'm going to consider the case where u is much smaller than w, where w is the bandwidth of the kinetic energy. And I'm going to claim that the solution I present is asymptotically exact in this limit. Okay, so if there are any questions, please feel free. But before I get into the details, I just want to summarize the bottom line. So what I find is that Tc is related to the bandwidth, and comes an it's the smallest expression for Tc you can ever imagine. It's e to the minus 1 over u squared, basically, times some number. Okay, that's what you find in the weak coupling limit. So the good news is that Tc is rapidly increasing with u. The bad news is it's pathetically small, right? In the limit where I have any control to do a calculation. Then there are corrections, and this is what I will call effective interaction from this definition here. And the solution is, in some sense, asymptotically exact in the sense that if you take the limit as u goes to 0 of this function, it is some number, alpha 2, which I can tell you exactly how to compute. Okay? So I've derived an explicit expression for this alpha 2, and when you calculate alpha 2, you get the pairing symmetry as a consequence. Okay? And from this alpha 2, also the pair wave functions are obtained. And you can also compute corrections. Okay, so...
Stick to S-wave pairing.
Sorry?
Are you considering the S-wave pairing?
No.
Not necessarily.
In fact, S-wave will never occur in this problem. Because the interaction is on site, and any S-wave will have an amplitude of being the trivial S-wave, which has on-site pairing, which is severely penalized by repulsive interaction.
Can I ask you this, a question concerning the summary? Because people were doing this stuff for decades, right? Just well-controlled, weakly interacting limit. And could you please update on in terms of what's new, what's old? Because maybe there were some errors, whatever. I remember at the March meeting when Kivelson was presenting this stuff, Alexandrov was trying to ask the same question, but in a sort of extreme form, in the form of a statement. Like, this is, everything is well known and stuff.
Yeah.
The reply of Kivelson was also commensurate to the question, like, it's not a question, it's a statement. And he showed his back to Alexander. But basically, I really want to ask the question rather to make a statement. So I really want to understand what was known, what was, whether there were some errors, mistakes, I don't know, and what's new.
Okay, so as you said, there's a long history to this problem. The first attempt is made by Kohn and Luttinger, okay, in the 60s. And what they do is consider a rotationally invariant system. And because of the sharpness of the Fermi surface, you have some non-analytic behavior at, say, in the susceptibility at wave vector 2kF that gives rise to oscillatory behavior in the electron gas, which mediates an attraction. Okay? So what I'm going to tell you is kind of an update of Kohn and Luttinger for lattice systems made in the language of renormalization group. And it is very much in that spirit of Kohn and Luttinger. Okay? Kohn and Luttinger
with the same results.
No, the results can be different. I mean, they are, if you apply the methods that I'm going to present to a continuum model in which the lattice plays no role whatsoever, then it does reduce to Kohn and Luttinger.
I'm just talking about...
But lattices were also done.
Sorry?
Lattice was also done.
By?
Chubukov, Kagan...
Okay, so what Chubukov does is... okay, so Chubukov is, if I understand correctly, looking in the limit of dilute concentrations on a lattice, where the small parameter is not U, but it's rather U times, say, the concentration of electrons. And then U doesn't have to be small. You can do an infinite order U.
Even better.
Yeah, so what I'm going to look at is where the concentration, the density is of the order of 1. Okay,
Well, this was the criticism which people gave to them. They do the solution
yes.
as if it's reliable in the limit of small density, but they have a solution. And then this solution, which is definitely correct up to U squared, was used to higher densities. That's how people were criticizing them. But the solution was there.
Okay, so what I'm going to tell you is, so the thing that's new here is what I'm trying to say is this expression is derived in the language of renormalization group. We introduce a cutoff and show that the final results don't depend on the choice of cutoff. Previous people have tried to do this, but their cutoffs were representing a physical scale in the problem. Say, if you're working at finite density, the scale of the problem was the deviation from half filling, for example. And then you're forced to work in a restricted range, either very close to half filling or, in the Chubukov case, in the dilute limit. But the result that I present here can be applied to an arbitrary lattice with an arbitrary concentration. The only requirement is that U is small.
Oh, do you mean that people were not consistent in doing small U limit?
As far as I know, that's correct.
Well, if you do small U limit near half filling, there is all sorts of problems that arise from competing channels.
That's only true if you're exponentially close to half filling, if you really fine-tune such that there's perfect nesting. But in the really weak coupling limit, competing orders don't occur.
Well, okay, so I happen to know exactly what I'm talking about. There's a big problem there of corners and so on.
Yeah.
You just cannot do a type of normalization group analysis that people would really like and that you can do in one dimension. So, but what I'm little that I know of this work, I think you will concentrate on superconducting. So you'll be in regimes where you have some assurance that the leading instability will be superconducting one in some channel.
That's generically the case. As I say, in the weak coupling limit, unless you fine-tune to a region where you can have instabilities in the particle hole channel, this is not the case. Superconductivity is always happening in the Fermi liquid.
Okay.
But we may talk about that if you have a disagreement.
Okay.
All right, so going back to the program. The basic calculation is, what do you need to do the calculation? You just need to compute from the band structure this non-interacting particle hole susceptibility. And from this, one computes TC by solving an eigenvalue problem. There's a matrix GKQ, whose row and column indices are momenta, points on the Fermi surface. And this GKQ, for example, in the spin singlet channel, is related to this non-interacting susceptibility. Okay? One diagonalizes this matrix and looks for the most negative eigenvalue. Okay? And there's another problem in the spin triplet channel, which is chi of k minus q, minus u squared. Okay? And then you simply diagonalize this eigenvalue, this matrix, look for the most negative eigenvalue, which I call lambda 0. And this number, which I call alpha 2, is simply the absolute value of the most negative eigenvalue.
So I missed the definition of G again.
G depends on, so I'm imagining I have inversion symmetry so that the spin singlet and spin triplet separate, decoupled. So there's a different G for singlet pairing. So there are some Fermi velocity factors, and it's U squared, essentially U squared times chi of K plus Q. And this is a matrix whose row indices, say, are K, and column indices are Q. So the hat means that the momenta live on shell, on the Fermi surface. Okay? And for the triplet case...
This is induced interaction, or what is this G? How can I understand this?
I'll get into it. It comes from doing our... doing the method, which I just wanted to give you the results first.
Okay.
But it's schematically, that's the one bubble in the particle-particle channel?
Everything is computed in the particle-particle channel, but there are... I'll make all this clear as we go on. Okay? Any questions? No? Okay. So that's the definition, and once you compute this number, alpha 2, which you obtain from this eigenvalue, the associated eigenfunction will be related to the gap function on the Fermi surface. Okay? And I'll get into alpha 1 later, but that's a technical thing, and I may not get into it if time doesn't permit. So before I derive the method, I want to show the application of this method to various systems. So let's talk about the 2D electron gas, first in the continuum. Okay? Let's have k squared over 2m. And in this problem, it's well known that the particle hole susceptibility is just constant, all the way from 0 to 2kF. Okay? So that means that if I have a circular Fermi surface, the effective interaction between any two electrons, any two electrons can only be as far apart as 2kF, and the interaction will be completely independent of where these two electrons are when they in the Cooper channel. Okay? So I'm doing Cooper scattering, and the effective interaction does not depend on the initial or final states. Therefore, this matrix is just a constant matrix, and it can never have any negative eigenvalues to this order. Okay, so there's no superconductivity at this order in U squared for this 2D electron gas. But on the other hand, if I applied a magnetic field and polarize the spins, then what you have is that in the weak coupling limit, the instability occurs in the spin triplet channel. Okay, so basically what happens is for electrons, so we're dealing with the Hubbard model, so the interaction is always between opposite spins. For electrons on the big Fermi surface, their effective interaction comes from the little Fermi surface. Okay? And for two electrons that are on the big Fermi surface, they can be at momenta larger than 2kF of the small one. So you can have a non-trivial pairing interaction. Whereas for electrons on the small Fermi surface, they'll always be, they will get their effective interaction from the large Fermi surface. And they will never have superconductivity because their wave vectors will always be smaller than 2kF of the large one. Okay, so what happens is that the larger Fermi surface develops a px plus ipy superconductivity of the spinless kind because there's only one spin flavor. And the smaller Fermi surface actually remains metallic in the limit that spin-orbit coupling is absent. And you can actually calculate this exactly if you define some ratio of the kf of the small Fermi surface to the big Fermi surface. The pairing eigenvalue is just u squared, the density of states, times eta 1 minus eta. So it's 0 when this Fermi surface is completely shrunk, it's fully polarized. It's 0 when it's completely unpolarized. It's optimal when it's half maximum polarized. Okay, so that's the continuum. If you look at a lattice system, this is for arbitrary concentration from 0. So I consider a square lattice with nearest neighbor hopping, t equals 1. Second neighbor hopping, t prime is 0.3. And you see that near half filling, there is a dominant superconductivity is dx squared minus y squared instability. And away from half filling, on one side, you have a px instability, and so on.
This is all repulsive interactions?
All repulsive, yeah. There's no attraction. There are effective attractions, which I'll get into, but the bare Hamiltonian that I study is repulsive. Okay. Are there any other questions? Then I'm almost done with the survey, and I'll get into the method. But if you also look at, for example, the Hubbard model on a honeycomb lattice. I know some, for example, Annika has studied this problem. What you find is that so these are the Fermi surface contours on a hexagonal lattice. Okay? So there's one regime in which the Fermi surface, so actually, sorry, I'm talking about the triangular lattice, but the honeycomb is very, very similar. Okay, so there's one regime at dilute concentrations where you have a single Fermi surface. Okay, in that regime, what you find is that there's a D plus ID superconductor. Okay, but then the system goes across a Lifshitz transition. There's a Van Hove point, and then one gets two Fermi pockets. And in that regime, you have an F-wave superconductor. And then we also looked at 3D systems such as the cubic, BCC, FCC, diamond lattice, and we find P-wave, D-wave, and F-wave solutions. We never find S-wave solutions. The P-wave solutions also occur in dilute concentration and can be thought of as the limit of the helium-3 problem, extrapolated down to weak coupling. And you
But
also
not
have,
in 2D.
Sorry?
But not in 2D.
Not in 2D, that's correct. Unless you apply a magnetic field.
Yeah, you explained. Yeah.
And then you also have D-wave solutions, which are doubly degenerate or triply degenerate. They are simple generalizations of what you get in 2 dimensions. Okay, fine. So now let me tell you what I actually did. Okay, so what we do is we do a 2-stage renormalization group procedure. Okay, the first stage is what we start with our bare Hubbard model, bare U Hubbard model, and we just do perturbation theory because U over T is small. Okay, so what we want to do is you integrate out all the states above some scale which I call omega 0. Okay, omega 0 it has no physical relevance whatsoever, and it only has to satisfy certain bounds. That is to say, it has to be much larger than this number, and it has to be much smaller than U squared over T. I'll explain this in a minute, but it's clear why it has to be larger than this. Okay, the reason it has to be larger than this. So let me just. So what we have is, for a given U, there is essentially U squared and e to the minus 1 over U. And for whatever U you have, you choose your cutoff, omega 0, anywhere in this range. Okay? This scale is where the bare ladder diagrams begin to diverge. Perturbation theory begins to fail. So you don't want to choose this cutoff to be too small. Okay? But you also, as I'll make clear in a minute, you want it to be smaller than of the order U squared over T, which turns out to be a very simplifying device in this problem. Okay, so going back to Boris's question, this aspect of this problem, making omega 0 unphysical, and then showing that the final answer doesn't depend on omega 0, as far as I know, was the contribution that we made. Okay, so that's first step. We just integrate out all states above omega 0. Then we started with a bare U Hubbard model. By integrating out those states, you get some k-dependent, but not frequency-dependent, as I'll make clear, a k-dependent effective interaction, which can have attraction, repulsion. That's that matrix G of KQ, which I diagonalize. Okay? So that's step 1. Then step 2 is I have this action with effective interactions that are defined in a narrow shell about the Fermi surface. And then that's exactly what Shankar and Polchinski studied in their fermion renormalization group method. So they have states in a narrow width of the Fermi surface. They can linearize the Fermi dispersion. They have irrelevant interactions that are small, and you can simply do one loop RG and calculate what the scale is at which some effective interaction in the Cooper channel begins to grow. Okay, so we look at the 2-particle scattering amplitude in the Cooper channel, which is marginally relevant. That leads to the BCS instability. And finally, the TC is the scale at which the flows begin to diverge in some channel. Okay, it could be P-wave, whatever the channel is. That's the most negative eigenvalue of that matrix, which I diagonalize. And finally, that scale will be independent of omega 0. Okay, so to be more precise, we think of some Grassmann path integral of the kinetic energy, and we have our U. And the first step is we simply do this perturbation theory and calculate this object here. Okay. So this is the scattering amplitude of an electron at k and minus k to state q and minus q. Okay, so this has zero center of mass. It's in the Cooper channel. And why do I only consider this? You can also consider states in the particle hole channel. And as Zlatko mentioned, those in the weak coupling limit, those are marginally irrelevant. They don't produce any large energy scales. There's no logarithmic divergence unless you're very close to some special points in the band structure. Okay? So that's what we compute perturbatively. Now, when you do this, so as I said, there's a decoupling between spin singlet and spin triplet channel. You can look at scattering between opposite spins in the singlet channel or between equal spins in the triplet channel. And for example, in the singlet channel, you have the gamma is the Baire interaction plus this interaction, which diverges logarithmically, but is independent of momentum. But the key process is this crossed interaction, this exchange interaction, which is not divergent, but momentum dependent. And then there are higher orders. Okay, so this is a well-controlled perturbation theory in U. And in the triplet channel, one finds the lowest order, it's just the U squared, another momentum-dependent interaction. Okay.
So the last guy is really the particle hole.
So this is all in the particle-particle channel, but
No,
this
I
is
mean-
the particle hole susceptibility.
I just mean in the S wave, last term in the S
This
wave.
one?
Yeah.
That's
Yeah.
just induced. Isn't it?
That's the induced interaction, but see, this is also in the particle-particle channel.
I think what Leo
just
had
think
in
about
mind
it.
is this is a cross diagram. So if you uncross it,
Yeah.
then you get your arrows going in opposite direction.
Correct.
Inside that
Inside
step of a ladder.
Yes,
Yeah.
inside the ladder, that's correct.
It's the kite, it's the
Yeah.
density
Yeah,
bubble, yeah.
yeah, exactly. And you get the same bubble here as well. Okay, so now, so I sort of lied to you, actually. When you do this calculation, you find this effective interaction depends on frequency. Okay? Now, that's the reason I choose my bounds of this cutoff to be smaller than U squared over T. Okay, why is that? Because, okay, let me explain this. So, if I have some interaction chi of k plus q, U squared chi of k plus q and omega, okay, this is going to be U squared chi of k plus q at zero frequency plus something that's of the order of omega 0, the cutoff at which I did my integration above it. Okay, but if my cutoff is smaller than U squared over T, then it's smaller than this term, and it can be completely neglected. And so that is the reason I choose my cutoff to be smaller than U squared over T.
Would you mind just repeating that? Please forgive me. I
Sure.
just did not understand.
Okay, so what I'm saying is I'm doing perturbation theory, integrating states above omega 0.
Yes.
Okay? The effective interaction is going to be frequency dependent, depending on omega 0. But I can write that as a frequency independent part plus some number that's of the order of the frequency.
And then you choose your cutoff so that number is small.
It's small.
Okay.
Exactly.
But let me just to clarify.
Yes.
So chi, that's the term which is most important to you,
Yeah.
right? Chi is definitely proportional to density.
Chi is proportional to the
Density
density of
of-
states.
Density of fermions, okay.
I mean, it's the density of states, right?
I know.
Yeah.
It's proportional to density of fermions as well,
Okay.
right?
Well,
Anybody
not-
who was
not-
doing
I mean,
If you are, well, I mean, so for instance, that small wave vector is just a mass into dimension. There is no
it depends
density.
on the model, right?
It depends.
I mean, it's
the model
of
you're
the
talking
order
about.
1 over T.
No, it's for sure 1 over T. I was just trying to say, okay, well, people who did calculations for small density, they definitely had the same.
I mean, I can compute chi at any density,
I know.
and
I'm
it doesn't
just-
increase.
I'm not saying
It doesn't
doing-
increase monotonically with density. I can guarantee you that. For
I'm
example,
not
if you
saying
have
it's
particle
increasing,
hole
but you're
symmetry.
just saying something I'm not even asking.
Okay.
I'm not saying it's increasing with density or anything.
Okay.
I'm just asking.
You're saying
whether
it's the
people-
density.
No, I'm just asking. First, I asked the question. I didn't say anything.
Okay.
I'm asking whether people who are doing calculation at small density, whether they had all the same terms at least. Maybe they had something else, assuming that you have to go to scattering length instead of Bain interaction.
Yes.
But they definitely had the same 3 terms which you have for gamma S, and they definitely had the same term for gamma T. Is it true?
Yes, and I think they probably had more. They're doing an expansion in KFA.
Okay, so if they had more, that's fine.
Yeah.
But they definitely had the first 3.
Probably, yes. Yeah. Okay. And also, by the way, Cohn and Luttinger had the same.
Okay. Am I right that RG is one of the methods which you can apply, but it's not necessary?
Well,
because it's all about summing a ladder.
Yeah, you want to sum over the most singular diagrams in this problem, and RG is just a way to do that.
One of the ways.
Yeah. Okay, so that's the end of the first step. And then we have, as I said, we have interactions just about this bandwidth omega 0 about the Fermi surface. Okay, so that's my effective action now, which looks something like this, which is this guy is computed perturbatively in the first step. That's the same kinetic energy. There are no self-energy corrections to the kinetic energy that are needed to solve this problem. And in the Hubbard model, they just don't occur to the order that I'm calculating. Okay, so that's what one has. And you simply, then what we did was we simply just wrote down the formula, transcribed the formula from Shankar's review. What you do is you take your cutoff and lower it by some flow, exponential flow, and I'll define this matrix, which I showed you earlier, to be this effective interaction times this Fermi velocity factors. So this is a Hermitian matrix. It's symmetric in K and Q. And the flow equation for this G is simply this. Okay, this is shown in Shankar's review, where this star product is simply a convolution of this moment. It's matrix multiplication, basically. Okay, but I can also work in a basis in which G is diagonal, and then what you find is that each eigenvalue of G simply flows separately. Okay, and then those eigenvalues are easily integrated, and you find that if there's no negative eigenvalue, there will never be an instability. However, if there is a negative eigenvalue, there is an effective interaction or eigenvalue which continues to grow. And the scale at which it grows to be of order 1 or begins to diverge is what I will call TC. Okay, so if you look at TC, it's this arbitrary cutoff that I showed you, that I defined, times an exponential of the most negative eigenvalue. Okay, but if you see this expression, it looks like it obviously depends on the arbitrary cutoff. So that's clearly there's a problem here. So that can't be physical. But what you do is, what we've done is we've gone and looked at this perturbation theory more carefully. And what one finds is that in the eigenvalue itself, there is an implicit dependence of omega 0, which exactly cancels the cutoff dependence. Okay, so let me explain what I mean by that.
Can you, before you do that, can you go back to the previous question?
Sure.
So, are all the problems you consider, you have the flow equation is just a matrix multiplication between G's?
Yes.
There's no, like if you consider a multi-band problem, there's nothing, it's always,
okay.
this,
no,
always can be written. I know problems in which this does not happen, you really have to,
that's a good
something
question.
other than the matrix multiplication, then you can't really solve it by the eigenvalue.
No, so if you have a multi-band problem, there will be a row and column index which is not just the momenta, but also Fermi surface 1, Fermi surface 2. So there will be an intra-Fermi surface interaction, there will be an inter-Fermi surface interaction. So you have to look at the most negative eigenvalue of that matrix as a whole. That's what one finds.
But it's still the right-hand side of the flow equation is a matrix multiplication in all indices,
yes.
wherever the indices appear.
Exactly, yeah. That's, as far as I know, that's something that's true for short-range interactions. I mean, I cannot guarantee that's the case for Coulomb interactions. This is a problem which I haven't studied. Okay. So let me explain why this cutoff independence can be how it can be understood. Okay, so as a simple illustration, let's go back to the negative U Hubbard model. Okay, where their interaction is negative U. Okay, so if I looked at this eigenvalue. To this order, it's just U, but if I went to a higher order, you would find that it's U plus a term which diverges logarithmically. This is G of k and G of minus k, that diverges logarithmically. And so when you look at TC, it's omega 0 times this whole matrix when treated properly. And you see this particular logarithm precisely cancels the prefactor dependence on the arbitrary cutoff. Okay, so then what we find is that TC is actually related to the bandwidth, W, times e to the minus 1 over rho u, which is what we know well from the case of the attractive Hubbard model. Okay?
Can you explain this a little more? I mean,
yeah.
so... I'm trying to understand what...
Okay, so this is U, and that's U squared times log, right? Log of the bandwidth over the scale, above which I do perturbation theory, integrate out states.
I mean, but this is the thing you resum to get into the denominator, or not? This is the first two terms.
Yes, this is just the first two terms in stage 1 that I do my perturbation theory. All I'm saying is that for every such term, there is another term that looks like this, which is logarithmically divergent. That although it's a higher order, you have to keep it in order to extract the dependence.
I mean, there's also log squared and so forth, but
sure.
That's a higher order correction.
Sure, that's a
correction to a prefactor.
That's not exactly. That's not a correction to the prefactor.
Oh, I see. But the Cooper instability is now a ladder infinite set of ladder diagrams. At least can be phrased that way in now in lambda naught.
When you do RG, yes, that's correct.
Now in lambda naught.
Correct.
Right?
Correct.
Okay, but I see.
Okay. So let me just illustrate in pictures for the more non-trivial case of repulsive interactions. So, for example, you can compute in the first stage perturbatively this dressed effective interaction, which is the bubble which I showed earlier, and then there are several others. I'm going to call this the triplet interaction. This parenthesis means it's of order U cubed. Okay, if you diagonalize this, again, you find the most negative eigenvalue, and you will find that TC depends on the prefactor omega 0. Okay, in order to remove this artifact, one computes this quantity, which now is of the order of, this is my g of t from above, and there's another term which has this logarithmic divergence. And if I take this term and do Rg on this, then what one finds is that the most negative eigenvalue, I've essentially extracted the implicit dependence on omega 0 in the eigenvalue. Okay? When I do this, this feature is immediately removed. And what you find is that Tc, again, is the bandwidth times e to the 1 over lambda 0. Okay. Are there any questions? I'm essentially done with the talk, but if there are any questions, I can pause. Yes?
I mean, I'm not familiar with what other people have done, but I guess you can also achieve cutoff independent results by just reformulating the thing in terms of the scattering length. What's the difference between what you've done and getting cutoff independent results, reformulating things in terms of vacuum scattering matrix elements?
Okay, I'm not sure. Okay, this is an extensive literature, and people have done many things. But let me tell you one thing that I know that has been done in the past, which is very similar to this. This is a two-stage procedure in which the cutoff, omega 0, is basically the deviation from half-filling, or deviation from a Van Hove singularity. This is done by Heinz Schultz and former student Janke. Okay? Then what you can do is, but there, omega 0 is a physical scale. It's some concentration away from half-filling. Okay? It's maybe the concentration of holes, for example. And then, you know, this omega 0 is a physical scale in the problem, above which the Van Hove singularity is important, below which it isn't important. Okay, but what I'm doing here is saying that omega 0 is completely arbitrary. And to be honest with you, I'm not sure.
It's just you said that there were some people who did this expansion in KFA, and I thought that A was the scattering length or something. And that should also be cutoff independent, but I guess I should.
Yeah, no, I think the work by Chubukov is correct. I mean, I'm not saying that that's not correct. It's absolutely correct, but I think it's only valid in the small. It's in the limit of dilute concentration of electrons. Okay, you can comment if I.
No, I completely disagree.
Okay.
They select diagrams, they throw diagrams which are high order in concentration. But they definitely have same diagrams up to second order in U, and even higher. So if you formally take the results and apply them to concentration of order 1, assuming U is small, they have the results.
Well, but if you look at his cross diagram, the structure of that diagram depends significantly on what is the concentration. In a limit of in a low density limit, it's going to have certain structure.
Yeah.
But if you are in a limit where you are closer to half filling, although not in the regime of Schultz and Zanke, then it's going to have some different structure. I think that plays a role in his calculation of eigenvalue. Is there?
No, but well, you see, people did if you have an answer which in a certain limit contains U to higher order.
Yes.
And it's for large U, it's done in the limit of small concentration. But if you simply take the formula, first in this formula make a limit of small u, which means you keep only terms up to 1 over u squared, and then apply those formulas to arbitrary concentration, you will get the same answer.
Well,
I'm simply saying this. That's what I'm saying. Just well, you have a formula.
Well, I don't disagree with you, but if you look at that, if you take that viewpoint, then von Lattinger calculation gives you the same answer too.
Except Lattinger didn't do it for the layers. That's what was said.
Well,
Chubukov and Kagan did it for the continuum and for the layers.
Maybe a delicate question to which degree the formula is general, because my understanding of what Zlatka is saying is that if you take, say, low concentration, you have one type of dispersion. It would be, say, parabolic.
yes.
If you have it like half filling or quarter filling, it's non-parabolic. There are cosines and stuff. So if Chubukov has some general formula for a general spectrum, then I immediately agree with you.
For the lattice as well, they discuss lattice.
They discuss lattice, but whether they derived a general formula in terms of the
So,
dispersion.
It may be formulated in
Let
the
me-
first few steps in general, but the final results, I'm not familiar with it, but it's possible that the final
Yeah, I
results
also remember.
are
Okay,
actually calculated for low concentration, so then you can't then go and stick high
Can
concentration.
I make a very quick
may I?
statement?
Okay, may I just say something?
By means.
So
You are the
we
speaker.
sent. Okay, this is not a direct answer in terms of physics, but we sent Chubukov this paper, and he didn't say that he had already done everything. Now that could be him being polite, or that could be something real.
No, I agree. Okay.
I could. That's
No, I agree.
that's
I
the level.
agree with Leo that probably
Yeah.
they had this set of formulas, but they never applied them to the right limit, and that's it. So they just don't have the answer.
Could be. I don't know. Actually, and also this framing in terms of the asymptotic expansion and looking at the next correction, as far as I know, hasn't been done even by Chubukov. Okay, and showing that it's a part of an asymptotic series. Okay.
But
You're now talking about-
It's a method rather than answer, because
It's a method,
the
right.
same answer can be obtained by different methods.
It's a method. Right.
Nikolai's comment was about the answer per se rather than.
That's a fair comment. I accept. Yes. You wanted to mention?
No, if you fully accept it, then I have nothing to say.
Okay. But what I'm trying to say is that this is the method is what I'm trying to highlight here. Okay. So let me conclude. So I say that the ground state of the repulsive U-Hubbard model in the weak coupling limit is a superconductor. Okay. And Tc is determined by the momentum dependence of the susceptibility. And the momenta over the entire Brillouin zone, not just at 0 or 2 kF, are important. And Tc is exponentially smaller than the bare energy scales. Above Tc, the system is just an ordinary Fermi liquid. There are no bad metals, spin liquids, nothing in this problem. And there are also no competing orders. There's only superconductivity in the weak coupling limit. So in order
Even
to
at half filling?
Okay, so if you want to access this order, you must fine-tune the band structure to be at, say, on a square lattice with no second neighbor hopping and mu equals 0. You can fine-tune that, but you have to do it exponentially accurately so that you can have competition between particle-hole channel and particle-particle channel. But, that's an interesting problem that you can actually analyze this competition. It's a fairly difficult and extensive problem. No one has done that before, even Chubukov, and it's worth looking at. Okay, and I just want to say, just as a comment, that we applied this method to one of the unconventional superconducting states that I mentioned earlier, namely the strontium ruthenate, and we constructed a new microscopic view of this system. We have a theory that explains some of the experimental mysteries, namely the absence of the electronic edge currents in this problem. But that's the subject of an entirely different talk. So if there are no questions, let me end here.
So I have a question.
Yeah.
So you say there are no competing interactions.
Yes.
And I'm guessing what you mean by that basically everything is superconductivity. Now, depending on a type of lattice that you look at and dimensionality and filling that you consider, there is, of course, many possible superconducting states. In principle, when you write your matrix G, you could look at many different channels. In principle, there's some point group of a lattice.
Absolutely.
You can expand things in spherical harmonics
exactly
to that point group.
Yeah.
So do you go all the way, or do you truncate at some point?
Truncate the matrix, you mean?
The matrix.
No, we look at the entire spectrum.
So you just basically take...
Yeah, but you see, the accidental degeneracies in this matrix are, essentially they never occur, unless there's some symmetry reason.
No, I understand.
Yeah. So, and since this spectrum represents the exponential, or the log of TC, there's essentially no competition between different superconducting channels either.
Well, that I believe. There is typically a leading channel, unless you are at some very fine-tuned point.
Right.
But it's more to the effect that in the end you compute alpha 2, was that the name of that number? Yeah. Is that alpha 2 in any way affected by, for instance, if I truncate it at this level or at that level, if I keep 4 members versus 12 members of my matrix?
It probably is, but I mean, we keep all the
you
entire
basically
spectrum.
keep all.
Yes, and we simply look at the most negative eigenvalue of that. So ignore all the other states. But you can plot the spectrum as a function of band structure, for example, and you can see where level crossings occur.
Okay, thanks.
A technical question. I mean, you are using Polchinski, Shankar, Gibsonian kind of renormalization group.
Yes.
Now, at the end of the day, what you're doing looks pretty similar in the sense to Morikawa-Simansky approach, because you're where you demand that the dependence on an arbitrary normalization group scale should vanish. That's the essence of the Gauss-Simansky equation. So what I'm wondering is that you have argued that you put your card off such that your perturbative result is not dependent on the omega 0.
Yeah.
If you then write an equation that just says the omega 0 on your equals to 0, would that give you
I think so.
this thing that you're looking at? That would be just a different way of formulating.
Yeah, I think that would. I think so. That's right. No, that's a good point. I didn't appreciate that. Yes.
I think I'm still kind of uneasy about necessity of having to break up this procedure into 2 steps. Fourth grain down to. I mean, so if I was doing things exactly, I mean, what is the qualitative difference between this initial coarse graining where I start at a physical scale, like the bandwidth, and I integrate to lower and lower energies, finally stop at omega naught, and then. I mean, if I was doing things exactly, I would think it's all one procedure. It's maybe because you're trying to connect it to an approximate scheme of Shankar that
so
you need to do it in 2 steps.
I agree with that. If you did it exactly, you will find at the end of the day similar results. But the problem is if you start at the energy of the bandwidth and integrate out states, you're going to generate effective interactions, some of which are irrelevant, but nevertheless they're large. Okay? Just because it's irrelevant doesn't mean it doesn't do anything, right? It's big. It's a big effective interaction. But by doing this, by integrating down to a very small energy scale, we're assured that the irrelevant interactions are completely small and can be negligible. So what you're proposing to do is actually what is done by the functional people who do something called functional renormalization group. Okay, so they start at the high energy limit and start integrating out states. But what they do is they have to numerically calculate this problem, but they don't do it quite right. They neglect the frequency dependence of the effective interaction. They neglect irrelevant interactions. So they have a flow equation that they derive that's only valid in the perturbative limit, but nonetheless their initial conditions are something like u equals 4t, for example. And
no, but that's separate.
Yeah.
I mean, why can I, suppose I stick to the u's much smaller than t limit.
right.
Then what is the difference between a perturbative, your initial first stage, perturbative stage in u over t, and a perturbative RG, where again, scale by scale, I track, what the, what the integration of scale, what effect the integration of a previous scale has on the new pi, if you wish.
You could do that. You have to be very careful. My only statement is that you have to be careful about irrelevant operators that make some contribution. If you can handle all the bookkeeping, then it's a perfectly fine way to do things. I agree. Yes?
Yeah, Mrs. Swan. I mean, did you then get that, do you see that D-wave superconductivity emerges from your equations in 2D systems? Or I guess that would be a nice result.
A D-wave superconductivity?
Yeah, the D-wave symmetry.
Yeah,
Does
near
that
half
win?
filling.
Or
Sorry?
does that win? Over
Oh
the
yeah,
other
and I mean, on a square lattice near half filling, it's by far the dominant. It's not just D-wave, it's dx squared minus y squared. That's what one finds in other methods. Spin fluctuation exchange and functional RG. All these methods agree with one another.
And what is different about Stone's reverse lag, which makes it P-wave?
What is different? I mean, that's a question of these results. I mean, the pairing eigenvalues are non-universal. They depend on band structure. So there's no simple answer to your question. I can tell you. So I mean, but the band structure is complicated. I mean, if you look at a 3D Fermi surface, right, a spherical Fermi surface, and you look at its susceptibility, it's peaked at q equals 0. Okay, so the dominant fluctuations are ferromagnetic.
Small q.
Yeah, so small q, and that's why in 3 dimensions, for k squared over 2m, say, Kohn and Luttinger found p-wave pairing. Okay, that's because the spin susceptibility is peaked at q equals 0. But on a lattice system, it has all kinds of peaks, and there's no simple answer to your question. It could well be a multi-band effect and consequence of many different interactions.
But in your work, which you're advertising here, you just assume that it's such that at least the P-wave pair.
No, I don't assume anything. So that's one of the
Comes from the band
advantages.
structure.
It comes from a band structure.
Comes out of the calculation.
But so it does come out of it also. You take the real band structure,
You
and
take
the calculation shows P-wave, but it's hard to trace what exactly in that band structure.
So
is
no,
P-wave.
there are details that are I can give you 1 or 2 details, okay? But maybe it's best if we talk personally about that. But there is a quasi-simple explanation, which I have, but maybe it's best to defer that to later.
Well, you already mentioned it. It has to do with the small wave vector in multi-band character. I think that's probably.
It's not the small wave vector character, actually. In this case, it's a nesting of near 2kf, which gives rise to some.
Okay. How large is kf?
Well, it's something like 2 pi over 3. Or something like this.
Okay. In a single band.
Yeah, I mean, it's a multi-band system. There are.
Okay. Okay. Fine.
But I can say that in our calculation, the interband scattering plays an important role.
Yeah, that's why I would naively imagine that's why you get time reversal breaking states.
Well, you can get a time reversal breaking states even in a spherical Fermi surface, right? I mean, you get the A phase.
You can. Yes. Okay.
Yes. A practical question.
Yeah.
Can you show us a phase diagram of Hubbard model in some very simple unit, say t prime equals 0?
Okay.
And just how would it look, just out of curiosity? So what do you suggest for the Hubbard model with t prime equals 0?
Okay. So in that limit.
For our education.
So let me do something like this is half filling and it's particle hole symmetry at t prime equals 0, right? So Let me just show you the electron side. And
So the x-axis is the filling.
is the concentration.
Concentration.
Okay? And let me call this temperature, or let me say...
Oh, no. Zero temperature phase diagram. Zero temperature phase
Okay.
diagram. So what you suggest for the zero temperature phase diagram.
Okay, so then let me draw it along the line. Okay? This, and the ground state is always a superconductor, except for this measure 0 point here, where you have perfect nesting, and probably the Fermi liquid.
D-wave superconductor.
Yes. So let me get into it. At half filling exactly, the method fails. It breaks down. Because the Fermi surface is perfectly nested. Okay, so but away from half filling, we have a dominant range of dx squared minus y squared pairing. And then there's intermediate concentration, which is dxy pairing. And if you go to order u squared, you will find that there's nothing in the very dilute limit. But if you go to order u cubed, you'll find p wave. That's the phase diagram.
Can you step to the side?
Yes.
And that P wave is now caused by P at Q equal to 0, I hope, is it?
Well, you know, in the dilute limit, there's no peak anywhere.
I absolutely agree, yes. That's when there is nothing there.
That's when there's nothing. Yes.
But when you dope a little bit.
Yeah, there is a slight change at Q equals 0. That's correct.
Okay, thanks.
And if we will add some U dependence, say if the y-axis is U, so just this corresponds to infinitesimal U.
Yeah.
And how would everything go as a function of U? Is the beginning or the phase diagram?
Well, I would say out here.
Yeah, it's U.
I would say out here, I mean, you would have an antiferromagnetic state that.
Okay, very good.
Something like this, and but you see,
Yes, you
I'm
cannot
doing
control. You
asymptotic.
cannot control finite U. It's understandable.
So I would say this is superconductivity, but I don't know how high it extends. In general, Tc as a function of U looks like this. Okay, that's my summary.
Yeah, but we're talking. And how about P wave? What would be the?
You're
the
very
shape?
optimistic.
What would be the
Much
shape?
smaller derivative.
What would be the shape of the curve?
No, I think it's fairly large.
And in terms of this
DC
boundary,
is exponential with 1 over U
The
squared.
magnitude is small, but it's growing large.
I'm just saying, the derivative is 0.
it's not the end of the story. So how
Yeah.
about this boundary between P wave and dxy? So how it behaves as a function of U?
Okay, so you know that cannot be obtained from RG. So because you see, what is RG doing? It's summing the ladder diagrams in the way you want to think about
You
it.
mean that you cannot extract the boundary between?
Okay, so let me explain. So what we're doing is extracting the quadratic terms, if you will, in Landau-Ginzburg theory. Okay, what you propose that I do is to look at terms like delta 1 squared, delta 2 squared, for example, the competition between the order parameters. They're higher order terms.
Yes.
But you know, I think we can assume that the standard BCS phenomenology applies here. So what you will find is there will be a first order transition.
That's okay, but what would be the shape of the curve? Can you predict the shape? Suppose it's the first order. What would be the shape of the curve?
I think that's what I would say.
Meaning that even
Because I don't know any better.
Oh, I see.
And this is based on a phenomenology
I
of
see. So
BCS.
basically, you see that there will be some finite concentration at which there will be.
There will be exactly.
Oh, I see.
Now, if you pump up T prime at half filling,
Right.
you still get dx squared minus y squared for some range,
Yes, for a huge
That-
range, actually.
for a huge range.
Yeah.
Does that range extend to a point where you would kill a spin density wave at small u?
At what concentration?
At half filling.
Yes, at half filling, your half filling is no longer special when you have T prime. So absolutely,
I agree.
the spin density rate is
No,
killed.
I agree. I agree. But what I'm trying to say, at some point, when you turn on T prime, there is
Yeah.
no perfect nesting
Yes,
for spin density. So at small u,
yes,
you just have dx squared minus y squared. You already answered my question.
right.
But what I'm curious
As
is
you
that
increase U.
as you increase u,
Yeah.
can you make a case that perhaps T prime in some realistic size helps reconstruct the phase diagram that one sees at V coupling? or moderate coupling.
Yeah, I think there will be a continuous transition, actually.
Because the argument was made that this can be done for electron-doped coupling.
Yes,
as you
that's
know.
right. That's right.
That in fact you can do quantitative calculations at recoupling with the T prime. There the sign of T prime is different.
That's right. That's right. No, I think there will be a phase transition from the superconducting state into an antiferromagnetic state. And there might even be a coexistence of antiferromagnetism and superconductivity.
Thanks.
Okay. No questions? No, if there are no questions, let's